Hello everyone. This is our fourth video for chapter 12, partial differentiation, and today we are going to talk about linear approximations and differentiability. We will start with linear approximations, linearization of a several variable function, but let us remember first linear approximations, linearization of a differentiable function of single variable. Recall that if f is a function from R to R, this is a function of single variable, we said f of x is approximately equal to f of a plus f prime a times x minus a, which is the equation of the tangent line at point A. If you have a function y is equal to f of x, and if it is differentiable at point A, which means it has a non-vertical tangent line at that point, and by definition of tangent line, we know that for the points near A, if x is a point sufficiently close to A, the value of f of x and L of x are very close to each other. So for examples where evaluating f of x exactly is difficult, we can take L of x as an approximation for f of x. So we can say if f prime of a exists, which means f is differentiable at a, then L of x, or just this case, it's a good approximation. Here x is near a. Okay, now let me write definition of linearization of a several variable function. Given a function z is f of xy, the linearization of f at AB is the following equation. L of xy f of AB plus partial derivative of f with respect to x at AB times x minus a plus f sub 2 of AB, that is the partial derivative of f with respect to y at AB, times y minus b. Okay, you see the linearization of f at AB is a plane equation like that. Now let me explain why we call it linearization. If you go back and if you look at the function of a single variable, you see if the function is differentiable, then we said that the tangent line equation will be a good approximation for the value of the function. Here we have L of xy, blah, 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 blah. If the function has a tangent plane, last time we have seen that the tangent plane equation is L of xy is f of ab plus f sub 1 ab x minus a plus f sub 2 ab times y minus b. This is the equation of the tangent line at ab for f of xy is equal to z if tangent plane exists. But in our previous video, we assume tangent plane exists and find equation of the tangent plane at a given point. We haven't mentioned existence of tangent plane, the conditions for existence of tangent plane yet. Now we can come to that point. I have another definition. F of xy is differentiable at AB if the limit as hk goes to 0, 0, f of a plus h, b plus k minus f of ab, or let me write all of them in parentheses, plus h times f sub 1 partial derivative with respect to first coordinate ab plus k times f sub 2 partial derivative with respect to second coordinate ab over the distance between hk and 0, 0, which is square root of h square plus k square is equal to 0. Okay, you see, here we said that if f is differentiable, then the tangent line equation will give us a good approximation around the point A. Tangent line equation at A, if it is differentiable. Right now, you see, we define differentiability for f of xy. We have such a limit. When we look at like that, it doesn't make sense a lot, but now we can explain it. You see, as hk goes to 0, 0, we have f of a plus h, b plus k, and we have such an expression in parentheses. What is that? Here you have, we define L of xy as f of ab, f sub 1 ab x minus a plus f sub 2 ab times y minus b. And here we have L of a plus h, b plus k. So, definition of differentiability tells us that as hk goes to 0, 0, the difference between f and L approaches 0 as the distance between hk and 0, 0 approaches 0. What does it mean? It means that the vertical distance between the surface and the surface and the plane at xy is very small compared to distance between xy and AB. And this is the definition of tangent plane. So this means that f of xy is differentiable at AB means C is equal to f of xy has a non-vertical tangent plane at AB. Okay, so being differentiable, okay, f of xy is differentiable at AB means f of xy has a non-vertical tangent plane at AB. Recall that of a single variable, we know f is differentiable at at a means it has a non-vertical tangent line at a. Okay, now, so you see that if f of xy is differentiable at ab, then L of xy, here as we defined, which is the tangent plane equation, if it is differentiable, then L of xy is the equation of the tangent plane at AB, is a good approximation for the value of f at xy, where fxy is close to AB. So let us use this on an example. See on an example. Find an approximate value for f of xy is sine pi xy plus ln y at 0.01, 1.05. Okay, we are asked to find an approximate value for function which is sine pi xy plus ln y, and the point is 0.01, 1.05, which is a point very close to 0.01, and 0.1 is a good point for us because we can find the exact value of the function at 0.1, 0.1, I'm sorry, not 0.1, and we can consider partial derivatives of the function, and we can evaluate partial derivatives at 0.1 easily. So we can get the linearization of f of xy at 0.1, and it can be useful for to get an approximate value for the function at the given point. So let me write what I said. It's convenient to use the linearization at 0.1, since the values of f and its partials can be easily evaluated. Let us evaluate the function at 0.1. At 0.1, we have sine pi times 0 times 1 plus ln 1. Okay, here we got sine 0, which is 0. The value of the function at 0.1 is 0. What about partial derivative with respect to x? Okay, we have function sine pi xy plus ln y. Remember how to compute partial derivatives. Y behaves like a constant. We will take the derivative with respect to x. So we got pi y times cosine pi xy plus ln y, and the value of the partial derivative at 0.1 is pi times cosine 0, which is 1, so we got pi. Okay, what about the partial derivative with respect to y? Here we have pi x plus 1 over y, derivative of ln y with respect to y is 1 over y, times cosine pi xy plus ln y. So if you plug in 0, 1, we got what? 0 plus 1 over 1 which is 1 times cosine 0, which is 1. So we got 1. Okay, we have found partial derivatives and we are ready to write linearization of f of xy at 0, 1. L of xy is f of 0, 1 plus f sub x 0, 1 times x minus 1 plus f sub y 0, 1 times y, sorry, I said x minus 1, but it must be x minus 0, I'm sorry, y minus 1, which is equal to pi x plus y minus 1. Here we are not going to show, but later we will see f of xy is a differentiable function easily. So L of xy is a good approximation for f of xy near 0, 1. F of xy is approximately equal to L of xy for xy is near 0, 1. Okay, so consider f of 0.011, 1.05, L 0.01, 1.05, and the function is pi times 0.01 plus 1.05 minus 1, so we get pi plus 5 over 100. It's approximately equal to 0.0814. Okay, so we got an approximate value for f of 0.01, 1.05 by using the linearization at 0, 1. Okay, so let us continue. Here we gave the definition of differentiability. You see, if you look at the limit definition here, we have f of a plus h, b plus k, blah, 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 over square root of h square plus k square goes to 0. And here, from this limit, one can derive that differentiability implies continuity. If a function f is differentiable at AB, then it's continuous at AB. You can easily show as HK goes to 0, 0. Sorry, as XY goes to AB, f of XY minus f of AB goes to 0. F of XY goes to f of AB as XY goes to AB by using definition of differentiability. Okay, so let us continue with a theorem which gives us a sufficient condition for a function to be differentiable at a given point. But before that, before writing this theorem, we need another theorem. You are familiar from Math 119. a mean value theorem, a version of mean value theorem for several variable functions. If partial derivatives of f are continuous in a neighborhood of the point AB, AB, and if the absolute values of h and k are sufficiently small, then there exist numbers delta 1 and delta 2, which are between 0 and 1, each between 0 and 1, such that f of a plus h, sorry, f of a plus h b plus k minus f of ab is h times f sub 1, partial derivative of f with respect to first coordinate, a plus delta 1h b plus k minus, plus k times f sub 2 a b plus delta 2 k. Okay, here we have such an equality. This is also a mean value theorem because the result comes from mean value theorem for single variable functions. Here we just need to apply mean value theorem twice for, we will apply mean value theorem for each coordinate. Okay, let me explain how. We have the expression f of a plus h b plus k minus f of ab. You can write it of the form f of a plus h b plus k minus f of a b plus k plus f of a b plus k minus f of a b. I haven't changed anything. I subtract f of a b plus k and I added again. So it's exactly the same expression. Here you see, if you look at these two, first coordinate is changing, second coordinate is b plus k, it's fixed. So consider f of x b plus k. You know, f of x b plus k is a continuous function. Actually, it's a differentiable function with respect to x. We consider its partial derivative with respect to x, which means if you fix y component, you'll get a function depending on x, and derivative of f with respect to x exists by the assumption, exists, and also it's a continuous function, is differentiable in the neighborhood of AB. So for x is between a and a plus h. So by ordinary mean value theorem from MATH119, there exists a number delta 1 between 0 and 1 such that f of a plus h b plus k minus f of a b plus k is h times derivative of f with respect to x at a plus delta 1h b plus k. Ordinary mean value theorem tells us that if you have a function which is differentiable on an interval from c to d, then there exists a value between c and d such that f of c minus f of d is equal to c minus d times value of the derivative at the point which is between c and d. Here we are applying exactly this. A plus delta 1h is a value between a and a plus h, since delta 1 is between 0 and 1. Similarly, as I said at the beginning, we will apply ordinary mean value theorem twice. Similarly, since f of a y is differentiable, so it's continuous, for y is between b and b plus k, there exists delta 2 between 0 and 1 such that f of a b plus k minus f of a b is k times f sub 2 a b plus delta 2k. And this is the result that we want to get. We have shown the equality. Okay. We prove this theorem. To prove another theorem, actually, we will use this result in the proof of the next theorem, which tells us the following. If f1 and f2, partial derivatives of f, are continuous in a neighborhood of AB, I'm not sure I wrote neighborhood correctly. Okay, probably it's correct. Of AB, then f of xy is differentiable at AB. Okay, the theorem gives us a sufficient condition for a function to be differentiable at a given point. If partial derivatives are continuous in the neighborhood of AB, then f of xy is differentiable at AB. Remember from last time, we have considered an example. Okay, after this theorem, I will write this example one more time. f1 and f2 may exist, but the function may not be differentiable at the given point. Still, it may not be continuous. Okay? yeah, something weaker than being differentiable. We have given an example of a function whose partial derivatives exist, but it's not continuous at the given point, so it's not differentiable. But here we are giving the sufficient condition to be differentiable. If partial derivatives are continuous in a neighborhood of the point, then f of xy is differentiable at AB. In other words, f of xy, z is equal to f of xy, has a tangent plane, non-vertical tangent plane at AB. Okay, let us prove this together. We want to show that as hk goes to 0, 0, f of a plus h, b plus k, minus f of AB minus h times f1 AB minus k times f2 AB over square root of h square plus k square is 0 under the assumption that f1, f2 are continuous in a neighborhood of AB. Okay. Consider the absolute value of the expression f of a plus h, b plus k, minus f of AB minus h times f1 AB minus k times f sub 2 AB over square root of h square plus k square. We need some modifications. Here we have f of a plus h b plus k minus f of AB. From the previous theorem, by mean value theorem, we have f of a plus h b plus k minus f of a b plus k is equal to this expression for some delta 1 and delta 2. Theorem tells us that f of a plus h b plus k minus f of ab is h times f1 of a plus delta 1h b plus k plus k times f sub 2 a b plus delta 2 k. Here you see. I'm just using this equality. Okay? Okay, and what else we have? We have minus h f1 ab minus k f2 ab over square root of h square plus k square. And here we have in h parenthesis f1 a plus delta 1 h b plus k minus f1 ab plus k over h square plus k square f2 a b plus delta 2k minus f2 ab. Okay, And since h over square root of h square plus k square and k over h square plus k square are less than or equal to 1, we have the inequality less than or equal to absolute value of f1a plus delta 1h b plus k minus f1ab plus absolute value of f2a b plus delta 2k minus f sub 2 ab, and you can easily observe that as hk goes to 0, 0, since f1 and f2 are continuous functions, these two expressions approach 0. So by squeeze theorem, we conclude the result. Our function, our expression is bounded above by a function whose limit as hk goes to 0, 0 is 0. So by squeeze theorem, we can conclude that the limit is 0. And we have this equality, these limits, since f1 and f2 are continuous around AB. Okay, this is the end of the proof. So here the important part is, right now we know if f1 and f2 are continuous in a neighborhood of AB, then f of xy is differentiable at AB, which means it has a non-vertical tangent plane at AB. So let me write the example from last time, recall the example. This is the example to remind you that existence of f1 and f2 does not imply in general that f is differentiable. We also need their continuous to conclude it's differentiable directly. Note that f1 and f2 may exist still. F may not be differentiable even it may not be continuous at AB. For example, the example from last time, f of xy is 2xy over x squared plus y squared if xy is different from 0, 0, and 0 if xy is 0, 0. We have shown last time in our previous video, we have shown probably in our second video for chapter 12, we have shown that f is not continuous at 0, 0, so it's not differentiable at 0, 0, but f1 and f2 exist at 0, 0. Okay? Okay, this is the end of section 12.6. In our next video, maybe it's a good point to stop. In our next video, we'll go back to section 12.5. We first did section 12.6. In section 12.5, we will begin chain rule for functions of several variables. Thank you for listening.